Please welcome to the stage your host, Matt Dobrogé.
Good morning, good afternoon, good evening, everyone, and welcome back to the Lattice Developers Conference. Today's our last day at the Developers Conference, but staying true to traditional Silicon Valley tradition, we saved the best for last. So today, we're going to be talking about the different applications that our low-power FPGAs can be utilized for end customer benefit. And kicking off today, we're going to have a discussion about the different types of applications that our low-power but highly powerful FPGAs can go and drive in the marketplace. So to kick off our keynotes today, we have Alina Ong, our Corporate Vice President of Software Solutions and Applications Engineering. Please give a warm welcome for Alina.
Thank you, Matt. Good morning and good evening, everyone. Welcome to day 3 of our inaugural Lattice Developers Conference. My name is Alina, and I run Software Solutions and Applications Engineering at Lattice Semiconductor. Now, I have been working with FPGAs for a really long time, but most of my experience, I would say, has been with larger FPGAs, at least 1 million logic elements and above. Now, since joining Lattice, I've had the opportunity to focus on smaller FPGA densities. And I must say, every day I am truly amazed and inspired by how these small FPGAs can accomplish so much in such tiny footprints and at such low power. So today, we will show you a few such examples of modern applications implemented in small FPGAs across 3 different segments: client computing, industrial automation, server security and control. Now, in all these applications, we will show the capabilities of FPGAs implementing functions such as image and video processing, deep learning inference, cryptography and security, and last but not least, what I consider bread and butter, control and connectivity. So let's take a look at the first application in client computing, computer vision AI. Broadly speaking, this is the field of AI which enables computers and machines to interpret visual information from images and videos. Now, computer vision is applicable in many different segments, but in client computing, this use case is very prevalent in devices such as your laptops, your monitors, your webcams, and so on. Now, these applications drive very stringent requirements: high accuracy yet low power AI inferencing. Why? Because a lot of these devices are battery powered. Different devices require different camera sensors. And every generation we do see requirements for higher resolutions as well as faster frame rates. Now, real estate is also pretty tight on this type of devices. So having a small, reliable form factor is also a key requirement. Now, these devices follow a very strict cadence of release every year. So how do we keep up with this demand? Now, with the flexibility of FPGAs, we can support multiple generations of innovation building on a single device, making FPGAs an optimal choice for this type of applications. Now, let's delve into the use cases of computer vision AI. What you see here are use cases based on human contextual awareness. So let's take a look at that. So for example, for security, locking and unlocking your notebook as you walk away and as you approach. Privacy, dimming your screen when there's an onlooker detected. So most of the time you want to use this kind of feature when you are in a public place. But in our household, with my 10-year-old, this is a feature that is enabled by default. Now, apart from that, power savings, battery life savings. Again, also dimming your screen when your attention is not on your screen, when you're turning away, doing some other things. And then last but not least, intelligent collaboration. These are features that I don't have to elaborate. Background blurring, smart zoom, all of us use this every day in today's virtual environment. Now that you have the background, let's take a look at the solution itself. What you see on the screen is a grossly simplified block diagram of the different functions in a notebook subsystem. Let's talk through the solution. The heart of a computer vision AI solution is the computer vision AI inference engine. So let's talk through the data path. So video data comes in through the camera and the camera sensors into the CV AI inference engine. Now this engine has been pre-trained, for example, to recognize a human face. So as it takes images coming from the camera sensors, it starts to process it, and once it detects a human face, it sends a trigger to the SoC through the I2C interface. The SoC takes the trigger, makes decisions, and sends instructions back to the subsystem through the USB, whether it is to control the camera, to control the display brightness, or to even control applications. Now, let's take a look at Lattice's AI solution. The yellow box, as you will see throughout the slides, indicate functions that are implemented in the FPGA. What we have done is implement a flexible and scalable 3D head pose architecture in this engine. Now, this architecture enables accurate determination of a couple of things. The position of your face in the screen, the orientation, how you're turning, and the distance as well of your face in the image or video. Now, the more accurate the model, the better the quality of results. So for example, if you are able to very precisely detect the angle of your face, you will then be able to dim your screen more quickly, thus saving more power. So the ability to design flexible adaptations of AI algorithms on FPGAs truly enable our engineers to optimize for the best power and performance. Now, besides the CV AI engine, we need to look at integration of ancillary functions as well, such as camera sensor interface. Now, what we have done in our small FPGAs are to harden the MIPI CSI2 PHY interfaces, allowing ingress and egress of video data through the FPGA. Besides that, we have also hardened the USB function in the device, allowing protocols such as I2C, GPIO, SPI to be tunneled through the USB physical interface as well as through the USB software stack. Next, every display typically comes with a TCON device or a timing controller device to manage the timing and control signals of the display panel. This can be used to control the brightness, the backlight, the refresh rate, and so on. Now, typically the control is handled at the OS level. But with an FPGA solution, we are able to bypass the host and the OS to directly control the TCON device. When we are able to do that, we also see an improved battery life savings. So as a summary, all these functions are subsumed into the FPGA, allowing you to consolidate your BOM, to reduce your TCO, and further optimize power. Hang in there, we're not done yet. So let's talk about another function, the image signal processing function. The function of an ISP is to essentially take your raw sensor data and convert it into usable images through improvements in the corrections and adjustments and enhancements and so on. Now with ISPs, you want to determine your features and your performance, and then you customize your algorithms correspondingly. Now, these ISP algorithms can be implemented either on software or on FPGA hardware. Now, when you implement it on FPGA hardware, you have the opportunity to implement a very flexible and scalable ISP pipeline. Essentially, you pick what you want to implement and you pay for what you picked. Now, FPGA implementations are also highly deterministic and low latency, allowing systems to be very accurate and very responsive. So to that point, very similar to the argument of the 3D head pose, you can take that advantage and turn it into power savings. So the result is essentially the FPGA subsuming all these different functions in the laptop subsystem, offering a fully integrated, high performance, low power computer vision AI solution. Now, block diagrams are of course very great for explanations, but nothing beats the real deal. So let me cap off this section by showing you the Lattice AI reference platform. The baseboard, we have designed the baseboard to have plenty of different interfaces, allowing you to explore not just vision AI applications, but also audio AI and etc. Now, the daughter card can be interchangeable to support different Lattice devices. In this example, we are showing you the recently launched Crosslink U NX device. If you look at the picture on the right, you can see how tiny it is. 3 millimeters by 7.5 millimeters in size. How amazing is that? A small device can implement basically all the different aspects of functions that I've just walked through in the computer vision AI solution. Now, let's move on to the next application in industrial automation. This is a very important segment for Lattice, and also one of my favorite segments because there are so many different ways to architect and implement the solutions in this space, thus making FPGAs highly, highly relevant. Let's start with the movers in the industry. Industry 4.0. Industry 4.0 represents a significant shift in how manufacturing systems operate, focusing on connectivity, focusing on data analytics, real-time data processing, and so on. Now, the type of applications that goes into Industry 4.0 environments include customized motor control algorithms in robotics, image and pattern recognition in machine vision applications, and the deployment of AI ML for predictive maintenance. Now, these applications demand real-time, high-precision edge computing because you want decisions to be made on the factory floor very rapidly. Deterministic, flexible, and secure connectivity, enabling seamless data exchange between the different components of the manufacturing environment, for example, the host, the controller, the nodes. Now, with computer vision and machine vision type applications, the need to support various types of camera sensors. And last but not least, energy efficient, sustainable, and secure systems. So by sustainable here, we mean that you can upgrade your solution without having to change your hardware. Let's take a look at where small FPGAs fit in this equation. So the chart that you see here shows the ISA 95 model developed by the International Society of Automation to provide a framework that allows various systems to talk to each other in a manufacturing environment. Now, small FPGAs have the biggest relevance in the bottom two layers, the L1 control systems and the L0 node systems. Before I show you the examples, let me also quickly mention OPCOA, a standardized communications protocol designed to offer secure and reliable communication up and down the stack. Why are all this important? We will show the relevance of FPGA solutions mapping to these models and these standards. Okay, let's start with level 1 controller systems. L1 controller systems are essentially responsible for the management, control, and monitoring of processes and machinery on the floor. What they do is they gather data from the node devices such as sensors and actuators and make those decisions. The block diagram that you see here represents the different functions implemented in an industrial controller system, as you can see from the diagram. There are many different functions, so let's break it up piece by piece. First and foremost, providing a baseline embedded system template, for example, running FreeRTOS on RISC-V. Now, once you have that, you can overlay software libraries and stacks, for example, transport layers like UDP or TCP/IP. Now, some of these transport layers can be implemented on FPGA hardware, right? This allows better performance and overall improving the system network performance. Apart from that, FPGA systems can also provide various kinds of security. For example, protecting against unauthorized firmware installations and upgrade, and also securing the network transport through perhaps hardened encryption algorithms. Now, to that point on network transport, FPGAs also have the flexibility to support various fieldbus protocols allowing flexible connectivity between the controller and the node. Last but not least, FPGAs can also offer flexible RAS implementation. So as a user, you can decide your reliability and your availability requirements, and then you can implement the right fault-tolerant designs and redundancy schemes to address those requirements. All right, moving on to the node system, an example in the node system, machine vision. Machine vision functionally is actually very similar to what we talked about in the prior section, which is computer vision AI. If you look at the boxes that are highlighted in blue, let's take it from right to left. Data acquisition through the MIPI camera sensors, the pre-processing of images through the ISP pipeline, decentralized AI processing at the edge. And once you have the data, you can essentially send those data to the controller systems that we saw in the previous slide through different types of protocols, whether it's UPC UA standardized protocols like TSN or proprietary protocols as well. In summary, with FPGAs, at every stage of the functional pipeline, you have the ability to optimize for power, for performance, and for cost. One last application is motor control. Motor control algorithms are used to essentially regulate and manage the operations of your electric motors. And different algorithms are employed depending on your performance requirements, the type of motor, the applications, and so on. Now, whether you want to implement a controller system that is open loop, a controller system that is closed loop, or adding predictive maintenance to your closed loop system, FPGAs are perfect for this type of evolving requirements and implementations, enabling you to further future-proof your hardware systems. Let me now show you the Lattice Automate platforms that we developed to enable you to evaluate the two devices here, the Certus Pro NX device and the Certus NX device that can be used to implement functions in the controller and node systems respectively. Now on to the last application, server security and control. Again, let's start with requirements. Increasing security threats are putting insurmountable pressure to better access control and authentication at all layers, not just at the device, but also at the firmware and software layers. So as firmware and software gets upgraded in data centers, data center operators expect zero downtime and persistent security during those upgrades. Other than that, platform modularity concepts have also become center stage in the last few years, basically enabling the deployment of BMC solutions and security solutions separate from the base motherboard. So let's talk through that. So first and foremost, let's take a look at access control and authentication of firmware that runs on the hardware in the servers, for example, on your CPU and your BMC. So the PFR solution is a solution that provides essentially a secure and trusted environment for firmware installations and upgrades. This solution not only verifies the authenticity and the integrity of the firmware during startup, but it also maintains persistent and real-time protection throughout regular operation. Essentially, you get 24/7 protection. Now, in the event of firmware corruption and compromised firmware, PFR solutions should be able to restore your firmware to a known good state. So the Lattice Sentry solution is one such solution. It is anchored on a root of trust FPGA, and it can accomplish all of this above and more. Now, moving on, let's take a look at how platform modularity is changing the landscape of data center architecture. So today's monolithic server has many different components, essentially on a very complex motherboard. So breaking up the motherboard into distinct pieces seemed like a good idea. DCSCM stands for Data Center Secure Control Module, is a standard that is championed by OCP, and basically it drives the decoupling of certain functions from the baseline motherboard. So what you see here are essentially two separate boards, the HBM board, which hosts the CPUs, and the SCM boards, which host the BMC and the security solutions. Now, when the boards are disaggregated, you need some protocol and some interface to make sure that the two boards can talk to each other. So functions such as aggregation, connectivity, and control are required to be implemented between these two boards. That's where FPGAs come in, and FPGAs essentially provide the fastest time to market, and with the evolving standards of this, DCSCM, it also provides insurance towards future upgradability. Now let's move on to let's zoom in into the DCSCM card. So in the DCSCM card, we have the opportunity to integrate both the SCM functionality as well as the PROD functionality into a single device, further consolidating your bill of materials and lowering your TCO. The picture on the right shows a demo that we just showcased at the recent OCP, essentially implementing the block diagram that you see on the DCSCM card. Now, last but not least, FPGAs are also good candidates to subsume the BMC functionality. What we end up having is a fully integrated, fully flexible server management and security implementation. Now that you have seen all different applications, let's take a look at the devices that enable them. The Crosslink NX device family for video applications, the general purpose Certus Pro NX and Certus NX devices for industrial automation, and the Mark devices for server security and control. Today's theme is all about how small these FPGAs are. So let's take a look at how small they actually are. I hope you are as excited as I am about the formidable capabilities of these tiny FPGAs. Now with that, I would like to conclude. All of you have attended the conference in the last 2 days and have heard about Avant. But I would like to emphasize that Lattice is fiercely committed to the small FPGA roadmap. Today, we have a rich portfolio of small FPGAs designed for the lowest power and highest levels of flexibility and integration. Now, before signing off, I'd like to share a small story. When I started building the presentation, I wanted to build a case to debunk the myth that small FPGAs, have very limited capability, hence tiny but mighty. But I hope that through this presentation, you have seen clear examples of tiny and mighty. With that, fellow developers, I ask you to join us in unleashing the potential of tiny and mighty FPGAs as we reshape industries and drive the next wave of innovation. Thank you very much. Let me hand this back to Matt.
Thank you, Elena. Thank you, Elena. That was absolutely awesome. I love to see all the applications that are possible on our small FPGA platform. And I encourage all of our developers to go to our Lattice Developers Conference portal on latticesemi.com and explore not only the different reference designs and different partners that are showcasing some of the things that Elena shared in the presentation, but also all the different demonstrations and modules from our different partners for our ecosystem. With that, thank you again for your time, and I look forward to seeing you in the next session.